Welcome to all in the lecture series of functional analysis. Now in this lecture we see the theorem about the range and null space. So the statement of the theorem is, let capital T be a linear operator. Then we have to show that the range of the linear operator is a vector space if dimension of the domain it is equals to n, which is finite. Then the dimension of the codomain, the dimension of the range set, it is also less than or equals to n. The null space is a vector space. We have to prove these three statements. So first of all we start with the linear operator, as here the given condition is only that the capital T is a linear operator. As capital T is a linear operator, we see in the definition of the linear operator, if capital X and capital Y be the metric spaces, let capital X and capital Y be the metric spaces, and capital T from X to Y. As here we are taking the domain as the dt. Capital T from script d of t to y be a linear operator, that is given. Be a linear operator, and we know that script r of t, it is the range of the linear operator capital T. As capital T be the linear operator, T is linear operator implies that by definition of the linear operator, the domain that is the script d of t is a vector space. It is given in the definition of the linear operator. The domain is a vector space. Also in that definition we have to given that the range, that is script r of t. The range script r of t lies in a vector space. Lies in a vector space, that is we have to given. And now in this theorem we have to show that the range is also a vector space. Now to show that the range is a vector space, to show that the range script r of t is a vector space, to show that the range is a vector space, that means here we have to show that it is closed with respect to addition and scalar multiplication. The range script r of t is a vector space. We have to show that script r of t is closed with respect to addition and scalar multiplication, that is we have to show. So we start with any two element of script r of t and scalar multiplication. To show that it is closed with respect to addition and scalar multiplication, we take any two element of script r of t. That means we are taking here y1 and y2, these are the two elements of script r of t, and we also take alpha comma beta be any two scalars, and then we have to show that alpha y1 plus beta y2, that is also the element of script r of t. If we are proving that alpha y1 plus beta y2, that is the element of script r of t, it gives that script r of t is closed with respect to addition and scalar multiplication. So we start with the element of script r of t. We take here let y1 comma y2 be any two arbitrary element of script r of t, and alpha comma beta be any two scalar. We are taking the any two arbitrary scalars, as well as we are taking the any two element of the range set. Now y1 is the element of the range set script r of t, and the range set script R of t, it is the set of all y such that y must be written as the image of some element of capital X for some x belongs to the domain, that is the script d of t. And as y1 belongs to the range set and every element of the range set is the image of some element of the domain, it implies that y1 is equals to tx1 for some x1 belongs to the domain script d of t. In the same way, y2, it is also the element of the range set script r of t. It also implies that y2 it is equals to tx2 for some x2 belongs to the domain script d of t. Therefore, from y1 and y2, which are the any two elements of script r of t, from these two elements we get the element x1 and x2. Now these are the two elements of the script d of t. Now here we are taking the alpha y1 plus beta y2. We consider this. For this we write down. Now consider alpha y1 plus beta y2. Now we are putting the value of y1 and y2. Alpha into the value of y1 is tx1 and the value of y2 is tx2. Now this is equals to alpha tx1 plus beta tx2. But we know t is linear. Capital T is linear, and as capital T is linear, therefore alpha tx1 plus beta tx2, that is equals to t of alpha x1 plus beta x2. And also x1 and x2, these are the two elements of the domain, and the domain script d of t is a vector space by the definition of the linear operator, is a vector space. As the domain is a vector space and these two elements are the elements of the domain, therefore here alpha x1 plus beta x2, this is also the element of the domain because domain is a vector space. Now alpha x1 plus beta x2, it is the element of the domain, and we know that the mapping capital T, it is from the domain to the range set. And therefore, as alpha x1 plus beta x2, it is the element of the domain. That means here alpha x1 plus beta x2, it is the element of the domain. Therefore, its image, that means T of alpha x1 plus beta x2. Now it is the element of the range set. That means here T of alpha x1 plus beta x2, it is the element of the range set. But here T of alpha x1 plus beta x2, that is nothing but alpha tx1 plus beta tx2. And therefore from this, if we give it the equation number 1, and from this here if we give it the equation number 2, we get that alpha tx1 plus beta tx2, that is equals to alpha that is equals to T of alpha x1 plus beta x2, that is the element of the range set script r of t. But putting the value of tx1, that is equals to y, that is alpha y1 plus beta y2, it is the element of the range set script r of t. That means here, that means for any, as y1 and y2 be any two arbitrary elements of script r of t, for any y1 comma y2 belongs to script r of t, and alpha comma beta be any two scalars we get that alpha y1 plus beta y2, that is also the element of the range set, and this implies that the codomain, that is the script R of t, is a vector space because it is closed with respect to addition and scalar multiplication, and therefore the range script R of t is also a vector space. Now in this way we prove the first statement of the theorem 2.6.9. Now after this theorem we have to prove the second statement, that if the dimension of the domain it is equals to n, then we have to prove that the dimension of the range it is less than or equals to n. Now to show that the dimension of the range is less than or equals to n, that means here we are taking the any set of vectors like this y1 y2 up to so and yn, and once again, and we take one more element, that is n plus 1. We are taking y1 y2 yn yn plus 1. Now these are all the elements in script R of t. We are taking all these n plus 1 element in script R of t, and when we show that this set is linearly dependent, it means that the set containing the n elements may be linearly containing the n element or less. Any set which contains n or less than n elements, this set may be linearly independent, and when that set is linearly independent gives us that the dimension must be less than or equals to n. So we start with the n plus elements of the script R of t. So we choose the elements. We choose n plus 1 elements y1, y2 up to so and yn plus 1 of R of t in an arbitrary fashion. That means we are taking any arbitrary n plus 1 elements of the range set. That means here, that is for each I, 1 less than or equals to I less than or equals to n plus 1, each yi it is the element of the range set. Each yi it is the element of the range set, and therefore this yi is written as the image of some element of the domain. That is yi it is equals to txi for some xi belongs to the domain script t of t for all I, and 1 is lies between 1 less than or equals to I less than or equals to n plus 1. And therefore here, as we have the elements y1, y2 up to so and yn plus 1. Now here we are putting the value of y1, that is the tx1, here tx2 up to so and here txn. Again here we have the value of yn plus 1, that is the txn plus 1. Now from this we are getting the elements x1, x2 up to so and xn and xn plus 1. Now these are all the elements of the domain script d of t, and therefore here from these n plus 1 elements we are getting the elements from these n plus 1 elements of the range set we are getting the element x1, x2 up to so and xn comma xn plus 1 in dt. Now these are the n plus 1 elements in dt, and here that means we are writing here that is for y1, y2 up to so and yn comma yn plus 1 elements of the range set script R of t we get x1, x2 up to so and xn comma xn plus 1 vectors. Actually these are the vectors. We get x1, x2 up to so and xn plus 1 vectors in the domain script d of t. That is from y1, y2 up to so and yn plus 1 vectors. Here we are writing here because range is a vector space as we prove here. That is from y1, y2 up to so and yn plus 1 vectors of the range set. We get x1, x2 up to so and xn plus 1 vectors in dt. And dimension of the dt, it is equals to n. As the dimension of dt equals to n implies that any set containing more than n vectors is a linearly dependent set, and therefore as the dimension of dt equals to n and this set x1, x2, xn plus 1, this set becomes a linearly dependent, and therefore implies that the set containing the element x1, x2 up to so and xn plus 1 is a linearly dependent, and therefore alpha 1 x1 plus alpha 2 x2 up to so and plus alpha n xn plus alpha n plus 1 xn plus 1 equals to 0 for some scalars alpha 1, alpha 2 up to so and alpha n plus 1, not all zeros by the definition of linearly dependent, not all 0. As these are not all zeros and here t is a linear operator, and we know that as t is linear and as capital T is linear and t of 0, it is always equals to 0, and therefore here we have this equation, that is alpha 1 x1 plus alpha 2 x2 up to so n plus alpha n plus 1 xn plus 1 equals to 0. We have t of alpha 1 x1 plus alpha 2 x2 up to so n alpha n xn plus alpha n plus 1 xn plus 1, it is equals to t0, it is equals to 0. And as due to the linearity, we can write down it is equals to alpha 1 tx1 plus alpha 2 tx2 up to so on plus alpha n txn plus alpha n plus 1 txn plus 1, that is equals to 0. Now again here for some scalars, this statement is as it is. For some scalars alpha 1, alpha 2 up to so on alpha n comma alpha n plus 1, not all zeros, and this implies that is we are getting here alpha 1 tx1 plus alpha 2 tx2 up to so n plus alpha n txn plus alpha n plus 1 txn plus 1 equals to 0 for some scalar, not all zeros. It implies that the set containing the vectors tx1, tx2 up to so n txn plus 1, this set becomes linearly dependent. Now putting the value of tx1, tx2, we are getting that is the set y1, y2 up to so n yn plus 1 is linearly dependent. And as the set containing the elements more than n is linearly dependent, implies that the dimension of the range, it is lesser than or equals to n. Because here as we are taking y1, y2, yn plus 1 be any arbitrary elements of the range set, and these arbitrary vectors of the range set are this set containing more than n vectors is linearly dependent, implies that its dimension must be lesser than or equals to n. And therefore here we are getting the result that the dimension of the domain is lesser than infinity, and that is if it is equals to n, then the domain of the range set, it is also less than or equals to n. From this example we also get that the linear operator preserves dependence, because here as we are getting that here we are we getting the n plus 1 vectors, that is x1, x2 up to so on xn and xn plus 1. And here we get that this set is containing the n plus 1 vector is linearly dependent, and from this linearly dependent set we are getting that y1, y2 up to so on yn plus 1, this set is also linearly dependent, and it is only because of the linear operator. That means linear operator preserve the linear dependence. These results also we get from this example also. And now lastly, in the last statement we have to show that the null space is a vector space. Again, to show that the null space is a vector space, we have to show that it is closed with respect to addition and scalar multiplication, and that's why we have to start with any two elements of the null space. So we take the any two elements. Let x1 comma x2 be any two elements of the null space script n of t. As these are the any two elements of the set of the null space script n of t, and we know that script n of t be the set of all x belongs to capital X such that its image must be equals to 0. And here x1 and x2, these are the two elements of the null space script n of t, implies that tx1 it is also equals to 0, and that is also equals to tx2. Now we are taking alpha and beta. Let alpha comma beta be any two scalars. Now consider t of alpha x1 plus beta x2. Again here we have to given that t is linear operator, and therefore it is equals to alpha tx1 plus beta tx2. Now tx1 it is equals to 0, and therefore it is equals to alpha into 0 plus beta into 0, that is also equals to 0. That means t of alpha x1 plus beta x2 it is equals to 0, and this implies that alpha x1 plus beta x2 it is also the element of the null space script n of t, and therefore the null space script n of t it is also a vector space. In this way we prove the theorem about the range and null space.